So OpenShift is based off of several open source technologies. The one that you may hear a lot about in the industry is something called Kubernetes. Kubernetes is a product that originally was developed in-house by Google to run their own data centers. It was open source several years ago. There are now many implementers that have taken that open source code and provide Kubernetes products. OpenShift is Red Hat and IBM's version of Kubernetes. So OpenShift is a distribution of Kubernetes. That being said, it is much more than just what is out there in the open source community. In addition to making it enterprise ready, OpenShift contains a lot of additional things that if you were to go with another vendor or with an open source version that you would have to do yourself. Things like enhanced monitoring and logging, certification of many different middleware and runtimes, and a lot of very nice developer tools and concepts there. So I'm going to hand this over to Andrew to talk about this slide.
Sure. So OpenShift is how we do the hybrid cloud. So the benefit of running this on IBM Z is it provides a unified experience for both developers and administrators to run applications across both their IBM Z and Linux One on-prem Big Iron, their on-prem distributed systems, and in the public cloud, all with the same tool set, the same infrastructure as code capabilities, and the same experience for both developers and administrators. And the demo that I'll show later shows us in action where we'll be deploying an application across both distributed and mainframe systems without changing our tool set at all.
And then, an additional benefit, especially when considering the IBM Z platform, is while this is running in Linux, and if you can see from the stack diagram, this runs on top of ZVM as the hypervisor. Through various IBM hardware technologies, you can still have fast, reliable access to legacy data in Db2 on ZOS through things like hypersockets and things of that nature. So it helps bridge the gap in a way between modern development practices and important systems of record on the mainframe. So this image right here is a poster from the Cloud Native Compute Foundation. This is a nonprofit organization that tracks all of these new cloud native, so to speak, technologies that are in the field. And I've seen this at customers printed out, wall-sized and put on the wall. As you can see, there's a whole bunch of stuff on here. There's a lot of different technologies that are evolving in the cloud native space that if you were to go on your own to do this, you'd have to wade through a huge amount of stuff. So in addition to what we've already talked about, one of the big benefits around OpenShift is that it takes all these and provides a curated solution based on the best in breed of technologies from all these different areas. And if you wanted to peruse this, cncf.io is the website for this foundation. So it helps because rather than having to wade through a vast sea of new technologies, it's a very curated, enterprise-ready solution from this. So let's talk about some of the core concepts behind this. So the first thing, and you hear this in a lot of our both marketing and technical materials, is that containers are a Linux function. They are an extension to functionality that is available in Linux. So we say containers are Linux. If you are familiar with Linux or get familiar with Linux, it's just a small step to understand what containers are. Now, what are containers? From a functional level, containers provide different purposes for different or have a different meaning for different parts of the organization as to what they provide. If you're an infrastructure person, they are they provide application processes on a shared kernel. So in contrast to virtual machines, which we'll compare later, they're smaller, lighter, and denser than say virtual machine deployments. And the tooling around them is such that they are portable across different environments, and that's really one of the killer features of this. For application developers, containers allow them to package their application, whether it be a Java WebSphere application or a C application or whatever, with all of its dependencies into a container, into a container image, a package that can be deployed easily to any environment in a matter of seconds or a matter of minutes, and is easily accessed, shared, promoted, and moved around. So one of the easy comparisons here is between virtual machines and containers. And virtual machines are probably, at least evolutionarily, the step before containers. So in a virtual machine, traditionally I might try one of these drawing tools here. You are virtualizing a representation of physical hardware. So you have to, all of the low-level BIOS and system functions, you have to have an entire OS, and all of that sits on top of a hypervisor. And generally you see this in one of two patterns. Either you see a virtual machine that has, say, one application on it, or a virtual machine that has multiple different applications on it. In the case of one application for virtual machine, that tends to be kind of wasteful, and you still have a high management burden for that. If you are, but the applications are kind of isolated from each other, so there's some security implications there. The other pattern that's fairly common is to layer multiple applications on top of a virtual machine to try and create density. But these applications on this virtual machine, there's no concept of isolation between these necessarily. What containers provide is they provide level of density as you would for sharing applications on the same virtual machine, but also put up walls between them. So they're both isolated from one another and dense and efficient. So but at a container level, oops, let me get off the pin here. You still have to manage all of this. In just a moment. And so that's where OpenShift comes in. So what OpenShift does is it takes these containers, which are isolated applications that are in a format such that they're easily portable, and takes care of the management of this. So when we talk about an OpenShift cluster, it is a collection of virtual machines or physical machines that manage the containers across a large number of worker nodes. So in this instance, each of these white boxes represents either a virtual machine or a physical machine. So you have, as part of the OpenShift cluster, some master machines that control everything, and then amongst all the different worker machines, they control the distribution of these containers and the management, the scaling of them, so that it's not manual action. Let me erase all drawings. Oops, and I want to go back. Bear with me one moment. Apologize, I've lost my place here. Now, when you hear about containers in the field, you often hear about Docker containers. So a little bit of history. Docker incorporated and their eponymously named product was an early innovator in this field of containerizations, and they set up kind of a standardized tool set that became very widely adopted. Eventually, that became standardized in something called the Open Container Initiative that created standards for containers across different Linux implementations of it. So you oftentimes hear people talk about Docker containers, and Red Hat OpenShift runs Docker compliant containers, but it doesn't use Docker internally. Again, all of these things are standards based. So it runs an alternative runtime called Cryo, which is purpose built for Kubernetes and for this this use case. And so, but you will still hear, and sometimes you even hear Red Hat or IBM folks talk about Docker containers, because the term has become kind of like Kleenex or aspirin, is genericized. But when we talk about Docker containers, it is a standard implementation. There are multiple implementers, and in OpenShift specifically, the implementation is called Cryo. I already showed this slide. So going forward, let's introduce some more terms. So when we talk about a platform like this, a container is the smallest unit of compute. So that's in the same way that when you have a virtual machine management system like, say, vSphere or ZVM, a virtual machine is the smallest unit that it deals with. So a container is, again, a construct in Linux that isolates an application process and provides a way to export it and to run it on multiple different machines. There's a distinction between a running container and then a container image. A container image contains all the binaries, all the configuration, all of that kind of stuff to spawn a container image. So for example, you might have a WebSphere container image that contains your application that is used to then create a running instance of that we call a running container. Container images are stored in a concept called an image registry. So for there are many examples of large public ones. One of the larger ones is Docker Hub. There's also Quay.io or Key.io if you speak British English, where people have created these container images for standardized components, again, like WebSphere, web servers, JBoss, Node.js, all these different application runtimes that people can then use. So, so an image registry is a system that manages and stores different images of containers. There's capabilities to version and name these in an image registry. And in OpenShift, we take containers, which is the smallest unit, and wrap this in another concept called a pod. So from this point forward, we're probably going to talk a lot about pods. And generally, the ratio is 1 container to 1 pod, but there are use cases where we fit multiple containers into a pod. And a pod is something in OpenShift that gets a unique IP address and has some other properties that make it advantageous. So pods are what are run on the OpenShift cluster. So this is a different diagram, but same as one that I showed earlier. Each of these red boxes here represents either a virtual or physical machine that runs Red Hat Linux. There are masters that control the whole thing, and then there are all these different worker nodes. And these worker nodes run the pods that contain the applications, and there's some icons in here to represent some of the different technologies that you could write. The cat is Tomcat, the leaf is Spring Boot, which is a Java platform, Node.js, etc. In OpenShift, there are then subsequent concepts of things like replication controllers and replica sets that control what pods are run where. So instead of saying, I want this pod to run on this machine, you instead tell OpenShift, I want to run 4 pods somewhere in my cluster, take care of it. and OpenShift takes care of it. And the replication controllers and replica sets deal with that. Deployment config is another concept. This controls versions of this. So I want to deploy a container image that represents my application version 1.0. You don't go configure that on the machine. You tell OpenShift, I want to deploy version 1.0 using one of these deployment configs, and it goes and does it. There are ways to inject configuration into these pods, so you can have a container image that is used as the basis for a container inside of a pod that is generic. So it could be your application, but your application that's not configured. And maybe it needs different settings for the different environments, dev, QA, or if it's running in Amazon versus running on-prem. Concepts called config maps allow you to inject configuration into container images and into running pods so that you can keep the same artifacts in different environments and tweak them per one. Secrets are similar. There's a way to, but are for data that is sensitive, like say passwords and all that. And there's some level of obscuring the data within them so that not everyone can see, say, a database password or whatever that the application might need. OpenShift also takes care of a lot of the networking components. So there's a concept called a service, which is a bit of an overloaded term, but that provides basically load balance names for a set of pods that are running the same thing. In this example right here, we have pods that are, say, the back end of a service, of a back end of an application. So maybe this is a REST or a SOAP layer that the front end user interface calls to interface with the database. All of these pods serve the same purpose, and this service abstraction here load balances between the different pods. And provides standard names for apps to talk to each other within the cluster. There's a concept of a route which exposes services onto external names so that they can be accessed outside of the cluster. So if I want to access my application, my web application through a particular URL, I have a route that connects up the pieces so that I can do so. We can also attach arbitrary persistent volumes to containers through persistent volumes and persistent volume claims. So if I have, say, an application that needs some scratch space or is has some storage needs that are that needs to be outside, we can connect storage types, iSCSI, Fiber Channel, NFS. There's a whole bunch of different providers for this. And OpenShift also has things that check liveliness and readiness of the application. So you don't have to necessarily, so there is a base level of monitoring of these built into the platform. So you can write liveliness and readiness checks to make sure that the application is alive and if it is ready, and there are actions, corrective actions taken on those if they fail. In addition to just running pods from kind of a management perspective, these pods can be organized into things called projects, which allow us to do administrative level role-based access control over who can manage different pods and various other things. And so that's a brief overview of kind of all the different terminologies. I realize that was a little bit of a whirlwind, but I think it will help. I'm going to hand it over now to Andrew Austin, who's going to hopefully help make these concepts more concrete by doing a live demo in a system. So Andrew, I'm going to pass the presenter over to you now. Let's see, make presenter. All right, Andrew, you should be the presenter now.
All right, thanks, Clark. So in the demo today, which I'll be doing as a live demo in Tempting Fate. We'll be deploying an application in both an x86 and an S390X or IBM Z cluster, starting with the exact same code in the exact same Git repository to show how easily we can manage applications across platforms with this. Let me go ahead and pull up my console here. Let's actually go ahead and make a change to this application first. So this UI is something called Code Ready Workspaces, and that's something that I'll talk a little bit more about later. But the short of it is that this is a cloud native integrated development environment. So this is a place where I can work on my code anywhere in the world I can access the internet. And this is running on my my distributed cluster right now, but in the future this will be extended to run on IBM Z. All right, so I'll just add a quick sentence to our index page here. And I'll go ahead and commit that to our Git repository. And we'll push that up to GitHub. So now from this machine here, which is sort of acting like a continuous integration machine would in an enterprise environment, I just have to grab that change and build my Java artifact. And this is a very simple application that's built on the Quarkus Java framework. So we've built an artifact that is just some jar files that are going to run in a container. And since that artifact is platform agnostic, we can actually push that to any cluster that we want, regardless of the architecture, by using the build system inside of OpenShift to take those artifacts and package them up into a container. I've already created what we call a build config, which tells the cluster how to do the build. And all we have to do is start the build. All right, and what this is doing is taking the directory I'm working in, which already has our compiled Java artifact, and pushing it up to the OpenShift cluster to be turned into a container image. In an enterprise environment, of course, your Java artifact would be published to something like an Artifactory or a Nexus repository. And we can see our build is running. If I pull up the web UI, and this is the OpenShift web UI, I can actually take a look at that build as it runs and get real-time log information from it. Though at the same time this is running, in the interest of time, I am going to flip over to another tmux tab, and we're going to run the same build on this other cluster that I'm also logged into. And this is a cluster running on IBM Z in the IBM Garage for Systems in Poughkeepsie. And I've created the same build config on this one. And I'm going to follow this build, so I'll have it output the logs directly to my console and wait for it to finish. Now, the container image it's building is based on the Red Hat Universal Base Image, or UBI. This is an image that Red Hat provides that's freely available, that has the base of a RHEL 8 user space in it, and that you can build your applications on top of. And since it's available for both the x86 CPU architecture and S390X CPU architecture, we can use it as a common base image for both of these platforms. So in this case, you can see it's building our application image with the S390X packages, whereas if we look at the x86 environment, it built them with x86 64 packages. And we could see on the x86 side, our build is completed. Of course, it got a pretty decent head start. And this has pushed an image now to our internal image registry. So I have the new latest tag, which was pushed less than a minute ago. And what we're going to do is create what Clark was talking about called a deployment, which will take that image and run as many copies of it as we want inside the cluster. This is what it looks like as an infrastructure as code artifact. Is a YAML file with our image and how many copies of it we want and what ports it's going to expose. You can also do this from the user interface, but through the UI. But in the interest of time, I'm just going to create it with a infrastructure as code artifact. All right, and now we have a deployment. And that deployment is building a pod. And this pod is in the container creating status. And we'll check on, and now the Z build is actually complete. So we'll go ahead and do the same thing on Z. First, we'll make sure we don't have an existing deployment. And I'm using the exact same YAML files between the two clusters to do this. So there's no need to have mainframe and distributed specific configurations, or even specific configurations necessarily between on-prem and the public cloud. All right. And well, not only is the deployment created, but the mainframe has already fully launched the application. And we're running on this side too. So now we have this application running. I've created some network constructs called routes to expose this application via our load balancers at the edge of the cluster. So let me just get that. All right, and we can see this is running in the AMD 64 cluster, running in this pod. All right, and we'll do the same thing on the IBM cluster. Okay, and we're running in the S390X cluster. Now let's say that you had a load spike and one pod wasn't going to be enough to service your application. You can also, since we have this deployment construct, very quickly change the scale of it. We'll change our scale for the demo app deployment. We'll go ahead and launch 5 instances of it now. See, 1 is running and 4 more are being created. Now, if we use the correct URL and look at that endpoint, we can see that we're now load balancing across these pods. And just that quickly, we've taken a single Java artifact and deployed it across clusters running on 2 separate CPU architectures, one of which has all of the performance benefits of the big iron, and scaled up this application in a round-robin load balanced manner. Now, hand presenter back over to Clark so you can continue showing the slides.
Thank you,
I
Andrew.
do want to. Yep. I do want to talk. Oh, sorry. Go ahead, Clark.
It's just make sure everyone can see the screen. But, go ahead, Andrew.
Sure. So I do want to talk about some of the future roadmap items. Today, we can, of course, run all of the basic Kubernetes functions on IBM-Z, but we do have some pretty exciting features coming down the line. First of all, in the near term for Z, we'll begin having Istio service mesh. Like I said before, those code-ready workspaces, that Cloud IDE, will be able to run natively on Z, in addition to new storage options. First, the local storage operator using local DASD storage, so you don't have to use your IBM flash arrays or NFS storage. And then we'll also be bringing release parity up with the x86, so you can run the exact same versions at the same times across your clusters, rather than there being a few weeks of lag. Midterm, we're talking about doing OpenShift container storage, which is our software-defined distributed storage platform on Z. So everything can be contained within the cluster. And also, instead of running it on ZVM, allowing you to run it on KVM on Z to reduce the total cost of ownership. And then finally, in the long term, we have something called installer provision infrastructure, which is a very simple way of building a cluster with a couple of commands. Currently, that doesn't work on the mainframe, since we have to build the Z-Linux guests and ZVM manually. But in the long term, that's expected to happen using the IBM Cloud Infrastructure Controller and its OpenStack-based APIs. Next slide. And then there's some exciting stuff happening in the code-ready workspaces front, and I believe Elton will end up talking a little bit more about this later. But today, Red Hat Code-Ready Workspaces runs on the distributed clusters and provides that Eclipse-based Cloud IDE to give you a unified experience for developers, regardless of what they're running on their local machine, anywhere in the world that they can access your network. And that's currently comes with OpenShift. Now going forward, in the very near term, that will be available to run natively on IBM-Z. But then IBM also has plugins for it that's called IBM WASI for Red Hat Code-Ready Workspaces. And that includes extensions for COBOL and PLI language development to allow you to use the same modern tools to develop mainframe native applications for ZOS. All right. And I'll hand it back over to Clark. Actually, I think next is just questions. So feel free to raise your hand or put questions in chat if you have any questions for myself or Clark.
Hello. I'm sorry, this is Frank. I just wanted to reiterate, first of all, thanks for such a great job, Andrew and Clark. And second of all, if you have any questions, everyone is on mute right now. So the best thing you can do is either raise your hand or put a question in the chat, and we'll be able to address them. But I think that was a terrific overview. Just looking, seeing if we have anybody who is not bashful. I don't see any hands raised so far, so you guys must have covered it pretty well. One more scan. Wait a minute, I do have one. Judy Amoroso, you are self-muted. So if you go off of self-mute, please go ahead and ask your question.
Yes, hello. Hello, Frank. My question is, we're sort of learning about the OpenShift, and I work with the parallel simplex in the mainframe application middleware. And my question is, we're talking about switching over from that with applications, but some applications have such a rate that requires more efficiency, where sometimes the parallel simplex seems to be a better option. So I just was wanting to get some feedback on what, what that thought process was with comparatively.
So I can take that one. So you meant parallel sysplex, right?
That's correct.
Right,
Yes,
right.
within the mainframe parallel sysplex with applications as they run.
Right. So we do have performance studies in the lab and even with clients where we migrated some ZOS workloads, so COBOL and well, in that case it was COBOL, to IFLs, so Linux on Z and OpenShift, and we got comparatively similar throughput results, but significantly lower MIPS consumption because we're not using GCPs anymore, right? And we also migrated to a modern language. In this case, it was Java. So it performs almost as well as COBOL does. So sometimes, from what I've seen out there chatting with clients, there's this misconception that moving from COBOL to Java will be slow, like they'll be 3 times slower, 5 times slower. But that's not true. In our case, it was like about 5 to 10% slower, but that was well within the SLAs. So you won't really lose much in terms of throughput here.
Okay, thank you so much. That answered what I was pretty much I was just curious on where the thought process was on that. So thank you.
You're welcome.
So anyone else, please don't be bashful. We have Clark and Andrew ready to field your questions. I know for a lot of the folks that may have a Z background, there's a lot of new stuff here. And so if you have even some basic questions, it's perfectly all right. I just collaborated with Clark and Andrew on a project, and I learned a lot in the last 4 months that I didn't know before. So I know there's a lot to learn. So is there anyone else? Doesn't appear to be. So I'm gonna say we're gonna declare victory on presentation number 1. Thank you very much. And I would say let's take a 5-minute stretch break, refresh our coffee, go ahead and take a biology break, and we will come back in about 5 minutes. For the Eastern time zone, that would be about 2 or 3 minutes past 11, and we'll jump into our next presentation with Elton D'Souza. But thank you very much, Clark and Andrew. It was a great job.
All right. Thank you all so much for the time, and I hope this was valuable.
Thank you. Take care, everyone.
And since I'm trying to see if I'm able to do the second presentation, I wanted to jump in and see if you guys can.
Now, in terms of what I do at IBM, I basically do what Clark and Andrew do from the Red Hat side. I do that at IBM, right? So I work with our clients. We've successfully installed OpenShift at more than 15 different clients since we GA'd. And that's quite impressive given that OpenShift just GA'd in February, right? Now, these aren't production-ready deployments. We're still in POC phase at a lot of these client sites, but that should just give you an idea of the interest out there. And we're talking large credit card providers, large FSS clients, retail, right, federal. These are the sort of clients that are doing OpenShift on Linux on Z today. So with that, I'm not going to go into too much of detail of what is OpenShift, because my Red Hat friends did a great job earlier on that. So OpenShift is available on Z. And if you click this link on here, you can actually get a free trial. So the trial is 60 days long, and we can work on extensions if you need it. Now, the recommended way to get OpenShift is through something called Cloud Packs, right? So this is OpenShift on Z. And for Cloud Packs, you would basically procure that. Once again, you can get a trial for that for 60, 90 days. You can extend it from your IBM team, right? And the Cloud Packs it's basically a combination of middleware and OpenShift. So it comes as a bundle and the operating system. So you don't really have to pay for Linux licensing. It's part of the bundle. It's included, right? because that's a question I get very often. It's like, how much do I need to pay for RHEL licenses for OpenShift? And the answer is, for Z, nothing. It's included. You're not paying for RHEL licenses because it doesn't use RHEL. First of all, it uses CoreOS, and CoreOS is part of the OpenShift platform, right? It's not a separately licensed product. In terms of support, it supports ZVM today, but we will have KVM support shortly. And we are also looking at some of the other integration points. So if you're familiar with ZCX and HyperProtect virtual services on Z, we're looking into support for that in the future, right? But near term, KVM is coming sometime, and we have ZVM today already, okay? In terms of platforms, you need Z13 and above to run it. And in terms of hardware, it's either FCP or DASD for CoreOS itself and OpenShift itself. And then in terms of a workload storage, if you have workload that needs to store state, you would need either NFS or OpenShift container storage, or any of the Spectrum products from IBM, Spectrum Scale, Spectrum Virtualize, right? So those are the options for workloads. So I'm going to skip the slide because they did such a great job today. I don't need to repeat what OpenShift is. And I already spoke about what what platforms are supported here today. If you have any questions about this or configuration, how many IFLs are needed, how much memory is needed, feel free to reach out to me. We have done this at several client sites, and we'd love to help you guys here. So coming to the Cloud Pak. So what are Cloud Paks? So OpenShift in itself is just a platform, right? You can think of it as being a distributed Kix. It's just a platform. Kix in itself is kind of useless. It depends on what you do on top of the platform, right? So whether you're deploying COBOL in a Kix region, Liberty in a Kix region, whatever your language of choice is, your middleware and your applications that are running on top of Kix is what really matters. So that's what Cloud Paks are. It's basically a bundle of middleware to solve specific business problems that is packaged with OpenShift. Okay. So if you want to do application development, let's say you're trying to modernize your COBOL code and you're trying to move to Java, you would use Cloud Pak for applications, right, as the name implies. It also comes with a DevOps pipeline. And in fact, that's the only Cloud Pak that comes with a DevOps pipeline out of box. And it integrates with the DevOps pipeline that you saw earlier in the demo. And as the other names imply, if you want data, so let's say you want to do something with Db2 in the Linux space, maybe you want to experiment with some other open source databases like Postgres or Mongo or Maria, or you want to do something with analytics, right? Because these days, they say data is the new gold, right? Or data is the new oil. It's basically the fact that clients are trying to get more business and more insight out of their data by doing things like data mining, AI, and ML. And that's what you would also get from Cloud Pak from data. A Cloud Pak for integration is around message queues, so MQ. And we also have other Kafka-based products like event streams. And then on the next pillar here, it's Cloud Pak for multi-cloud management. Now, one thing you realize here is that this, 2020 is all about hybrid multi-cloud, right? We have different public cloud providers working together. We have platform as a service providers working together to provide the option for the clients to run anywhere that they want. And one of the neat things about OpenShift is it's really the only platform as a service out there that can run anywhere, literally. It can run on public cloud in any cloud provider, it can run on any private cloud provider, on Intel, or it can run on Z and Power, right? No one else can do that. Now, when you deploy so many clusters all over the place, you need some sort of management for that. And that's where Cloud Pak for multi-cloud management comes in. And Red Hat has a product called Red Hat Advanced Cluster Manager. So there is some change in the roadmap there where they're going to get merged and included and stuff in future. But right now, this is one of the Cloud Paks we have there for multi-cloud management. The cool thing about MCM is it will also integrate with the new ZOS work that we're doing for OpenShift, right? So it's not just OpenShift on Linux, it's also ZOS integration. And the last one here is Cloud Pak for automation, which is around BPM tooling, really. So this is a list of Cloud Paks, and as we just GA'd OpenShift in Feb, not all of these Cloud Paks are available today on Z. They're partially available, and that's all just driven based on client demand, right? Some of our clients, like they don't really care running, you know, a back end of an antivirus server or something on Z, right? They don't care about that. They want to do stuff that matters to their core business, right? So things like Liberty, MQ, Db2, that's the sort of stuff that is available today or will be available in the next month. And that's why we don't have all the cloud packs. We have the most important pieces of the cloud packs. And on the next page here, we actually have details on what's included in the cloud packs. So if you want something and it's not in here, just reach out to Frank or myself, and we can help you get it to the cloud packs. Okay. So that's it about the OpenShift side. Now we're going to jump into more of the OpenShift integration with Z. So if you saw the picture that that my colleague showed earlier, right, with OpenShift running on any platform, this is a much more detailed version of that. And you can see that a Z guy created this deck because Z's taking most of the space on this page on the left side here. And these are all the integration points that we have with ZOS and DB2 today. So when our clients ask us about, you know, what do you recommend for modernization? You want to modernize, how do we do that? Depending on their starting point and their end goal, we combine these products. And typically, you know, 2 or 3 of these are enough. You don't need all of them. And it really depends on the use case. So we're not going to go into all of these today, right, because we do have limited time. But if you do have interest in, you know, what these are and why you'd use them, once again, just reach out to Frank or myself, and we can, you know, go into details there. Okay. But the key here is OpenShift is the single control plane for all of this, right? Whether you're in the public cloud, you're on-prem on Intel, or you're on-prem on ZOS or Linux, OpenShift can be that single control plane. And that way, if your developers or your organizations complain about, you know, lack of Z skills, right? They don't need to complain about that anymore, because can they do OpenShift? If they can do OpenShift, they can deploy workloads to ZOS, right? So that's the sort of abstraction we're talking about here. And that is enabled through some of the stuff on the left here, like the Cloud Broker, like Ansible, like Vazi. So we're going to go into a little bit of detail there and how that relates to DB2. So first, before jumping into, you know, the ecosystem, I want to talk about why would you want to do OpenShift on Z. Okay. So this is a test we did back when OpenShift 4.2 was out. This was like the first release we had for OpenShift back in February. These numbers have improved significantly because OpenShift 4.5, which is the latest, performs about 4.5 to 5 times better than 4.2 on Z. Okay, so these numbers are significantly better today. But even back then, even with how inefficient 4.2 was, you can see that for this specific workload, which is really a Liberty-based workload talking to DB2 and ZOS, OpenShift was 37% cheaper end-to-end, right? This is everything: hardware, software, licensing, service and support, floor space, power, everything into consideration. It was 37% cheaper. And a lot of this comes from the fact that the licensing for OpenShift is actually very favorable for Z, because the way it works is you have something called virtual processor cores or physical cores, whichever is less. Now, it just so happens on Z, our physical cores are really powerful, right? IFLs can do a lot of work. So when you look at virtual cores to IFLs, typically IFLs are significantly lower than the virtual cores. So we're talking, you know, 10-to-1, 15-to-1 consolidation ratio. So that's the main reason why it's significantly cheaper to run on Z. And as you'll see later on, we have some clients who have workload that has no affinity to ZOS. They just want a cheap place to run cloud-native workloads. And Linux One was their answer, which is the Linux-only mainframe that we have. So this number is for Linux One. So this is a Linux-only mainframe. If you aren't familiar with the Linux One brand, it's something we released in 2015. And from a hardware perspective, it's pretty much the same, right? Same instruction set. You know, you connect the same DASD, same FICON, everything is the same there. But from an offering perspective, you know, IBM released Linux One so that we can give our clients this completely different, you know, Linux-focused offering that has a much more favorable pricing model for Linux-only workloads, right? And this is one example of why that's better. It's about 10 to 15% cheaper than running this same exact thing on a Z15. So a lot of our new clients who can't spell Z, they've never worked with IBM before, they don't know what a mainframe is, they just reach out to IBM for IBM, help us to run a cloud native solution on-prem, and we recommend OpenShift on Linux 1 to them, and they have no problems with that because they don't need to know about green screen, they don't need to know about EPSIDIC or any of that, right? OpenShift hides that complexity, as you saw in the demo earlier, and it's much cheaper because of the favorable pricing model. So in terms of a topology of what this would actually look like, you'd have your DB2 on the right-hand side here, right? DB2, KIX, IMS, vSAN, they'll all be on the right-hand side here. And then this is what OpenShift looks like. And once again, we're not going to go into the details here. I just wanted to kind of show you what the topology would look like. And we typically have an OSA adapter between the ZVM and the ZOS side of things. And you could also use hypersockets here, right? And hypersockets reduce latency even further. So the question that was asked earlier around, what's the performance impact? From a throughput perspective, 10 years ago, there was a performance impact. We were like 3 to 5 times slower on Java on Linux, for example, than COBOL on ZOS. But recently, with our new numbers that we have, Java's come a long way since then, right, on the platform. And you can achieve similar levels of throughput, but you will have higher latency. Okay, so we can't defy the laws of physics, right? So when you deploy let's say you're moving your COBOL code to Java microservices in Liberty, maybe compact applications on OpenShift, you might have an increase in latency that might be around 20 to 30% increase. Now, if you use hypersockets, that would improve. And in future, like next year, really, we're going to have something called SMCD support, right? That's shared memory communication direct between ZVM and ZOS. And that will reduce the latency even further. But if you're looking for the absolute lowest latency, I would still recommend sticking with deploying Java in a KIX region on ZOS, talking to DB2 or IMS or vSAN. Okay, so throughput, no problem. Latency, depending on your SLAs, you might be better off just keeping it on ZOS, right? And like I showed earlier, you can still use OpenShift for the ZOS side of things. Even though OpenShift doesn't run on ZOS, it integrates with some automation frameworks on ZOS. So end users will think that it's just any other Linux system out there, but in reality it's ZOS. Okay. So moving on to some client examples, right? What are some clients doing with this? This is one of the first clients we deployed OpenShift on. In fact, what's interesting is this client deployed the upstream open source version of OpenShift called OKD. They deployed that last summer before the Red Hat acquisition of any of that, right? And that's how long they've been working with this client. And recently, because of the Red Hat acquisition, we have OpenShift on Z. We migrated all of that to OpenShift 4.2, and these are the numbers they were seeing, right? 7.3 times lower latency for their communication between ZOS and their microservices compared to when they have it on Intel, right? And once again, this is all because of the laws of physics, right? We're not doing any magic here. This is just reduced path length from the network, and because of co-location, we get these amazing latency numbers. What's also interesting and not on this deck is that we've been working on a pricing model for this, and because we can stuff way more containers in an IFL, and the latency is so much lower, the pricing model for OpenShift for this client was also significantly cheaper than OpenShift on the distributed side. And they've been doing that for 5 years now in production, right? So the original reason for this work was to reduce the latency, but we realized that it's actually cheaper too. So it's not just the performance benefit, it's also the cost benefit, right? So they benefited from both of those. So this is one client, and this is in the financial service industry, more in the credit card processing space. And then these guys are planning to go to production by end of the year, right? So this is one success story. This is the other client. So this client actually ran out of space on the Intel side on-prem, and they have been in OpenShift also for about 2 or 3 years now, but they have several thousands of Intel cores, right? I'm talking like 6-digit number of cores, and they're just running out of space. And because of server sprawl, it was becoming very difficult for them to manage that environment, even with OpenShift, right? Because you have to manage the physical servers and the data centers. So for them, Linux One was a very attractive value proposition because Linux One is really a data center in a box, right? A box has about 171 IFLs, and with a 10-to-1 ratio, and with SMT2, we're talking 1,700 to 2,000 physical cores worth of workload on one Linux One box, right? So if you do the math, they could consolidate 30,000 worth of Intel cores down to 17 boxes, the size of a refrigerator. So they could consolidate 1.5 data center into something the size of your living room. So that's a huge reduction in terms of floor space there, right? While still getting the same SLA, same performance, same everything, right? So that's another example of a client that didn't really care about performance. They just wanted a more efficient place to run OpenShift on-prem, and Linux One was that answer. So coming into more of the ZOS integration part of things, we have something called Db2 for ZOS Datagate. So what this does is it runs on OpenShift, but when we have business logic running in the Java side of things off the mainframe, there's a huge problem there around making sure that your latency is lower, and some of the clients end up caching the data. When you cache the data off platform, you're going to end up with issues in terms of cache coherency. So your data might be stale, right? The other problem is in terms of transactional integrity, you have a problem because in a CICS region, you can manage your transactions no problem, right? But as soon as your data leaves the platform and you have transactions out of the platform, it becomes really hard to manage your transactions and committing end to end. So Db2 for Datagate solves that problem. And this is a relatively new product, right? It just GA'd in June of this year. So what this does is it runs on OpenShift, and it's actually part of the IBM Cloud for Data. And with this, you can cache your Db2 data. So if you're looking to reduce your MIPS consumption, so optimize your TCO for ZOS, you could use Datagate. And you would just access your Db2 Datagate instance as if you were accessing your ZOS instance, right? So no changes at all needed to your source code. That stays the same. You just change your IP address and port and credentials, and everything else just magically works. And then your MIPS consumption just goes down, right? So here's one exciting product that's very relevant to Db2. And this is available as part of Cloud Pak for Data. The other tool is the ZOS Cloud Broker. So before I jump into what this is, let me tell you the client problem that this is trying to solve. Okay, so about 2.5 years ago, we had this product called IBM Cloud Private, right, on Z, and that was actually our Kubernetes-based PaaS, and it was actually a competitor to OpenShift. Now, the problem with ICP and even OpenShift back in the day was, well, it only runs on Intel, and even when we did port it to Z, it only worked on Linux. Now, for that specific client, they wanted to improve their developers' dev test experience. So as a developer, if I want to go in there and deploy a new test environment, like let's say I want to deploy a new CICS region and deploy some Liberty, logic in that, it was very hard for them to do it because they had to send an email to a sysprog, and we all know how busy sysprogs are. Okay, they're super overwhelmed in terms of the work because everyone keeps on sending them requests, and typically the ratio of developers to sysprogs is pretty bad, right? Like at our IBM lab in Canada, we had about 4,000 people and 1.5 sysprog. I said 1.5 because that half was focused on other stuff too, right? So that was the kind of ratio we're looking at. Now, to their credit, they automated everything, so they didn't have to do everything manually. But if they had the Cloud Broker, they could. So that's really the problem that this solves. It's how do you deploy, how do you automate the deployment of things in the ZOS space? And things could be kicks regions, could be Db2 schema, could be stuff in IMS, could be ZOS Connect. All of that can be automated using the ZOS Cloud Broker. So when our clients talk to us about modernization, our first step there is, how do we modernize in place, right? Let's give them a quick win, quick reduction in time to value. How do we optimize the developer experience first before thinking about migration, right? We'll get to migration, but first, let's try to solve the problem with just modernizing in place. And this is one of the tools we use there. So with this, the developers on that client side, they took down the time of deployment from about 1 month down to about 3 minutes, okay, for a dev test region. That's a huge reduction, right? From a month to a few minutes, huge reduction. So it worked so well there that we decided to make this into a product. And then we had other clients saying, oh yeah, we had that same problem, right? So that's how these other use cases got added in here. So the Cloud Broker itself has 2 components. It runs on OpenShift. So it uses some of the Kubernetes building blocks. In this case, it's something called the operator framework. And then it connects to Db2, or well, not just Db2, it connects to ZOS. Today, using ZOSMF, right? The ZOSMF management framework. Later on in the year, it will use the Ansible for ZOS, right? And you can use either engine. So what that does is, if you go into the OpenShift GUI, you can just click on a button there to deploy a test region or to deploy code, and it will look like you're deploying a container on Linux or on Intel. Okay? So they won't even know it's ZOS. And it completely gets rid of the need for that sort of manual process from sysprogs, and it really optimizes that development cycle there. Now, of course, security is important, right? So this does integrate with RACF and all of the stuff that you care about in terms of security. So it's not just anyone can do anything, right? Security was one of the most important things when designing this. But it does give you the flexibility to automate. So this is the other really powerful tool. It's very popular with our clients these days, and especially with the clients that love ZOS, but don't necessarily like the development experience of ZOS, right? So this fixes that gap. And here's some more details about the broker. And once again, we have a trial for this. We have a trial for everything on this deck, right? And the trial's quite flexible. It could be 60 days, 90 days, could be a little bit longer too. And with these trials, you actually get pro bono support too. So we actually help you with installing it and integrating it with existing workloads and everything, right? So feel free to reach out to Frank if you want more details on this stuff. And one of the last things I'm going to talk about today is ZCX. Okay, so this is yet another integration point with Db2 on ZOS, and this solves another problem. So if you've been to any of these developer conferences, open source conferences over the past 5 years, there's a lot of cool technology that they talk about. They talk about things like Mongo, Kafka, Spark, Node.js, Nginx, Redis, all this cool stuff out there, but none of that works on ZOS. It could work, right? With a little elbow grease, it could work, but none of it works out of box, right? From, let's say, GitHub or from that actual ISV. But at the same time, these products offer a lot of value in the context of a ZOS environment, right? So for example, some of our clients, they wanted to use Mongo as a cache for some data on ZOS. Other clients wanted to use it as a cache for ZTPF data. So that's one example of a workload that's very beneficial to our clients on ZOS, but it doesn't run on ZOS. So we wanted to solve that problem. And that's where ZCX came from. It stands for Z Container Extensions. What this lets you do is it lets you deploy Linux containers. So the container that was built earlier in the demo, you could actually deploy that container on ZOS without any changes using ZCX. Okay, and what that gives you is 2 things. So first, the workload deployed in this is zip eligible, so you don't have to worry about burning your MIPS because it's zip eligible, and it's just like IFL pricing, right? It's much cheaper than using GCPs. So it's a cost benefit and TCO benefit there. Second is latency. So remember I mentioned the laws of physics earlier? When we move workloads from OpenShift on Intel to OpenShift on Z, talking to ZOS, there's a significant reduction, right? We have seen anywhere from 7 to 12 times reduction of latency. When we go a step further and move it from OpenShift on Z to ZCX on Z, talking to ZOS, you can imagine, because if it's part of the same operating system, right? It's just another address space. The latency is even lower. So from what we have measured internally, it's anywhere from 15 to 30% lower latency, right? Which is quite huge if you think about it. Especially if you're trying to do some sort of in-transaction type stuff, like in-transaction fraud detection or something, and you have really tight SLAs. Like we have some clients who have 10 millisecond SLAs, 5 millisecond SLAs, right? ZCX becomes very attractive there. So this is something else that we have in this sort of toolbox of cloud native. And today, the integration point between ZCX and OpenShift is through an Ansible operator, okay? Because ZCX, it just exposes a SSH and Docker, right? So we used the Docker playbook for Ansible. And if you're not familiar with Ansible and playbooks, it's just an automation framework that's used on the Intel side. And playbook is the word they use for, sort of like a recipe, right? What should this automation do? Kind of like your ZOSMF templates, same thing. So using the Ansible playbook for Docker, you can connect OpenShift and the Ansible operator, you can connect OpenShift to ZCX. So we can go a next step in terms of that demo and deploy that workload on ZOS without any changes, okay? So that's the integration point between OpenShift and ZCX. And we have a lot of clients using this for managing some of their Db2 data, for caching some of their Db2 data. And 5 years ago, we didn't have Kafka on Z, right? But it's just written in Java. It took us like 2 days to port it. Now we do have Kafka on Z. But back then, ZCX would have been great too, right? So that's one of the last tools I have here. Now, in terms of other interesting stuff that we're doing, we do have something called the Kubernetes on ZOS project. And that is native Kubernetes. So, how would you add a Kix region or Kix, for example, as a worker node to Kubernetes, okay? Now, we don't know if that's going to integrate with OpenShift, right? It's just sort of a skunkworks project. But if you have interest in, dealing with Kix regions or IMS control regions, any of that sort of stuff from Kubernetes, right? Using just typical, kubectl command line stuff, reach out to us because we are looking for people interested to try the product out, interested in sponsor users. So that's another project. It's super early days there. We're still in the design phase about, what should be a container, what should be excluded from it, how do you deal with security, how do you deal with multi-tenancy. It's still early days, we're still designing that, but that's another pretty cool project we're working on in the cloud native space. So with that, that's the end of my presentation. This is a very exciting time, in my opinion, for Z, where we sort of take the best of both worlds. We take what Z is good at, which is transactional workloads, data serving, high performance, low latency type stuff. And we bring in the user friendliness of the cloud through OpenShift, right? And one of my favorite phrases out there is, cloud is not a place. Cloud is an experience. And with OpenShift, we bring that experience to Z. So with that, I'll open up the floor to questions.
Thank you so much, Elton. That was awesome. It was very condensed, but I think right on point for the types of questions that I think people who are new to this would have. We're going to do the same thing that we did last time. I see a question that got posted in the chat from Tammy Hale, a once and hopefully future colleague, and she asked, is Linux One the new name for Z Linux?
So Excellent question. So short answer, no. So first, we never liked the word Z Linux in the first place, because when you use the word Z Linux, people think that it's some special distribution of Linux that IBM owns or something, but it really isn't, right? So on the Linux side of the world, we have Red Hat, we have RHEL, we have SUSE, right? And we have Ubuntu, right, from Canonical. Those are the three I'd call, enterprise grade, though really it's more about RHEL and SLES on the platform. And we do have others. We have, Debian, Fedora. We have these other things that also run on the platform, but they don't have enterprise support, okay? So first, we don't use the word Z Linux. We use the word Linux on Z because people get confused with Z Linux. Okay, so that was the first thing there. Now, in terms of the connection to Linux One, Linux One is a separate box. So how you have Z15, you had Z12, Z13, 14, 15. Linux One is a completely separate box where we announced the first box back in 2015, which was based on the Z13 hardware. But it was a different box. And if you ever get a chance to look at one, or you can just Google a picture, back then, the main difference was that the lines on the box on the Z13 were blue. The lines on the Linux One box were orange. Okay, so very simple, very basic visual difference there. But the main difference between them is the pricing model between them and the offerings on them, right? So you cannot run ZOS on a Linux One box. You cannot run ZTPF or ZVSC or any of these other things on Linux One box. It's purely for Linux. You can run ZVM, KVM. You can run Linux natively on the LPARs. And when I say Linux, it could be RHEL, SLES, Ubuntu, or some of the other stuff, right? So I hope that answers your question.
That's great, Elton. I think you did. So I'm scanning again, and Timmy says thanks, by the way. Any other questions for Elton about his presentation? I did want to let all the presenters know who are still hanging on that our attendance has held pretty steady throughout the presentation, which is always a good sign of engagement. So we're pretty much with the same number of people who started out with us at 10 o'clock Eastern this morning. So I'm not seeing any other questions, hands raised, or questions in the chat. So Kim, should we do another 10-minute break, or would you like to go directly into your portion of the presentation, gathering requirements for replication tools?
Well, I do have one question before we go any further. Question for Elton, just because I know that your nickname is the Wizard, and I certainly get the sense that you are one of those IBMers that says, yes, we can do that. Can you explain to everyone here when you started being called the Wizard?
Sure. So this is back in 2015. It actually goes back to the creation of Linux One. So back then, we had this launch event that was going to happen as part of the Open Source Summit. It was August back then. It was like August 15th. And our CTO for Linux One, Marcel Mitran, he came and said, hey, you work on all this cool stuff, because I was playing a lot of open source back in the day. He's like, you work on all this cool stuff. Can you build us something that will show people the value proposition of Linux on Z, right? To show people the ecosystem, how cool it is. So, I was in Toronto back then. So I went to IBM Research at IBM HQ in Yorktown. And I don't know if you know Donna Dillenberger. She's an IBM fellow. So I was there for about 3 weeks designing what could be a pretty cool demo. And then I built something over a weekend there, and then I showed all our executives and everything on the Monday, and they were like, "Whoa, this is like they just didn't expect what they were just like mind blown, right?" and that's why Donna, she's like, "Yeah, Elton's just a wizard. You just give him something, he'll just like pull something out of thin air and make it happen." And if you look at the video on YouTube, if you Google Linux One demo, you'll see it. It has about 200,000 views, I think, by now. It's one of the most watched videos of Z ever. It is the most watched video of Z ever. So so that's where the title came from. And since that day, it's stuck because Donna's a fellow. It's like the highest technical title at IBM, and she's pretty influential there. So she calls me Wizard, and now even our clients, they refer to me as Wizard. It's like, hey, you know, let's just get a Wizard on the call and he'll solve the problem. So that's how it's stuck.
That's wonderful.
Yeah, that's a great story. And you must be very pleased at that. So thank you again. I think you demonstrated your chops again today. Kim, I'm going to volley it back to you. Would you like to continue, or should we give these people a stretch break?
I think we should do a stretch break, because what we may do is come back in 10 minutes, and my session is very brief. And after my session, I think we can go straight into yours if you're ready. And that way we'll probably finish up a bit early, which never hurts anybody's schedule.
Okay, that sounds good. So right now I have 11:50 a.m. Eastern. So top of the hour, if we could come back together again, stretch break, coffee, whatever you need. And then we're going to go into Kim's presentation on replication tools, which you estimate to be about 10 or 15 minutes with some polls. And then I have my presentation that'll wrap up the day. Sounds
perfect.
Good. Thank you. Yeah. So we start the recording, and welcome everyone for the last presentation of the day, Mainframe Modernization Field Notes. Although I got reproved for using Mainframe Modernization because that turns people off. And then I heard Elton say, we don't call it Z Linux. And I was trying to do a really fast find replace for Z Linux, which is all throughout my presentation. So this is obviously a work in progress right now. I want to go through this fairly quickly. I think I really appreciate the fact that so many of you have hung in here. We still have just about the same number of folks who started the day with us. So I'm going to go through these slides. I like an interactive presentation, so I will pause at the end of a section to get people's feedback and any questions that you might have, and then there will certainly be an opportunity to do that at the end. As Kim said, this is gleaned from a specific customer engagement, and it was a learning curve for me. I was working with a lot of folks and a lot of technologies that I had not worked with before. But the thing that I found interesting was my knowledge of System Z, where I've spent 30 plus years of my career, was of value to these other folks because they didn't know anything about what we did on System Z. So these are the things that I found are important for people who do know System Z to be able to share with their colleagues who don't. So if you get involved in a project like this, these are the things that people need to be aware of. And if I could steal something from Bonnie Baker, these are the things I wish I had told other people at the beginning of this project. So this is our agenda very quickly. We're going to look at the System Z platform at a high level. We're going to look at System Z data sources. Again, this is going to be more review, but these are things that I'm calling out, not that you don't know, but the other people who are working in Linux or in containers or in data ops may not know. We're going to talk about different ways to get the data into DB2. And just as a caveat here, the purpose of this presentation is the expectation that the data originates in System Z and will continue to reside in System Z. We have lots of people's projects that have been working on, as Kim just said, of moving data into Kafka or into other repositories off platform. The design paradigm here is that it starts and ends in Z and may make a couple of stops along the way. Data source considerations, things that you need to know about if you're working with mainframe data, and then finally putting it all together. I'm not going to introduce the Fillmore Group anymore. I think we've done enough introductions, but I will kick off with System Z platform. So again, in terms of review, ZOS started out as MVS or MVT, I think, in the dark ages of about 35, 40 years ago. And it is a legacy mainframe operating system. ZVM also runs on System Z, and that's a hypervisor. One of our earlier presenters used that term. And basically, a hypervisor is an operating system that runs other operating systems. So under VM, I can run VM. I can run ZOS, ZVSE, and what I unfortunately referred to as Z-Linux or Linux on Z, as Elton would prefer. There is a native operating system for ZVM, Conversational Monitoring System, CMS, and now Red Hat OpenShift runs under ZVM today, and as was pointed out earlier, will eventually be able to run in its own LPAR. Again, also in terms of review, Z-Linux, there are 3 major enterprise distributions of Linux: Red Hat Enterprise Linux, SUSE, and Ubuntu. Now, I want to talk a little bit more about processors, because I'm not sure that everybody who has worked on System Z for a while understands this. The first processor that I mentioned here are known as general purpose processors or central processors, known as CPs. And this is what typically run ZOS workloads. So if I'm running CICS, accessing VCM files, I'm running all that on the CP. The capacity of the CPs that you are running on your mainframe determine your software costs. The more capacity of CPs, the greater the software costs. So IBM, a long time ago, started on a project to introduce specialty purpose processors to allow you to shift workloads from CPs onto other processors. And they are here in the dotted line box below: Integrated Facility for Linux that runs, not surprisingly, Z-Linux workloads, the ZAPs that run Java workloads, and the ZIPs that run eligible Db2 database workloads. Now, the interesting factoid that you may not know is that all of these processors, all 4 together, are identical. The only difference is microcode changes, firmware changes that disable certain instructions on the IFL, ZAPs, and ZIPs that don't let it run ZOS, for example. But otherwise, they're exactly the same. But by shifting workloads to these other processors, you can actually save a lot of money. The third thing that I want to talk about in terms of the System Z processors was mentioned a couple of times by Elton, and that is hypersockets. Hypersockets are an internal messaging system, communication system that I refer to as a skinny TCP/IP stack. So if you think about TCP/IP that we're all using today to look at this presentation, there is a lot of error handling and an overhead transmitting out over a wire or via wireless protocol to be able to get your computer connected to the website that GoToWebinar hosts this presentation on today. When I'm working with hypersockets on System Z, I have a bunch of operating systems that you see listed there that are co-located. There's no reason to go out over a wire. This is significantly faster to be able to communicate than it would be if I were going to have ZOS communicate with a x86 box somewhere else in the same data center. So it's efficient and secure internal network for all System Z workloads that are co-located on the same frame. And it uses cross-address space memory transfer using the memory bus. I'm not going out through the OSA card to communicate the way I would with an x86 box or even a power box someplace else. So putting this all together, this is a mashup slide that shows at the very bottom layer the different processors. You can see the CPs, the central processors. You could see a couple of IFLs in the gray space here. You may see zips and zaps. Up above that, you can see the amber colored long rectangle, which are the hypersockets that are communicating between all those. And then in the dark blue, you can see the operating systems, whether it's ZOS or Linux for System Z or ZVM in the sort of green shaded boxes. But this is an overall description of how all of these artifacts, all these different components, operate together in System Z on the mainframe. So with that, I will, I see a couple of questions up. I see a hand raised, so let me go to the questions. Let me see, it says, it looks like Frank has 2 screens, need to share the other screen. Ed Lynch, what are we not seeing? Are you not seeing my slides right now? Let me go ahead.
Yes.
Go ahead.
So Frank, I think the display settings at the top there.
Yeah.
We are seeing the presenter view, not the. Yeah, if you click on that, you should be able to switch.
Duplicate slideshow?
No.
Okay.
So if you do that again and just hit swap. Oh, there we go. Yep.
Yep.
Is that better?
Yep, that's it.
Okay, good. So I'll just stick with this one. Any other, let me see, I see a hand raised. Let me see. Oh, that was Ed. So I guess you were just pointing out the problem. Okay, yeah, sorry about that in terms of the presentation. Let me get this out of the way. Okay, so next I'm going to move on to ZOS data sources. And the first is IMS, Information Management System, very old hierarchical IBM mainframe data management method. Hierarchical, and I'll give you a diagram in a second, but IMS is still out there, still running transaction processing systems like ATMs and banking systems throughout the world, and probably will be doing it for a long time to come. It is extremely fast, optimizing the same transaction over and over again. I put in my card into the ATM machine, I type in my PIN, I specify I want to get an account balance or I want to make a withdrawal, and it happens. And those types of sort of bite-sized transactions that I want to do over and over again in a highly optimized fashion use IMS. And we can see here that different attributes are collected together in a segment, and you can see a collection of segments here in a hypothetical hierarchical database model for IMS. The second is VSAM, Virtual Storage Access Method. There are three different types of VSAM files: entry sequenced, key sequenced, and relative record data sets. The one that I've used the most and are probably the most common are key sequenced data sets that are indexed. So if I have a purchase order, I can find the purchase order I need by the purchase order number pretty quickly. This, like IMS, is typically accessed through a 3GL like COBOL or PL1. The challenge with a VSAM file is that the schema is embedded in an application. One of the glories of the relational database like Db2 is that the schema is externalized in a catalog and that schema is enforced. Whereas with a VSAM file, I have a copybook that is embedded in my COBOL or PL1 program that describes the file. As anybody who's worked in the space for any amount of time knows, that can cause a lot of problems because different copybooks in different programs can have different views of the data. Keeping them all consistent is a challenge, even with very methodical change control. And the most important is that a single file might have multiple different schemas. So an example that I'm going to use later in the presentation is that I can have both the purchase order header and purchase order line items embedded in the same VSAM file. And by having all that data together, it's a very efficient way to be able to access that, because as I scan the data, the purchase order number will be the same for both of those record types, but the data will be vastly different. Purchase order header is going to have the name of the vendor and the address and the phone number and those types of things. And the line item are going to have things like the line item number, the SKU number of the product that's been ordered, the unit cost, the extended cost, those types of things. So you navigate that in a COBOL program. But it becomes a lot harder if someone opens a file and sees a whole bunch of data in a whole bunch of different formats that aren't used to that style of programming. The next thing that I want to call out is that the physical sequence of records might have meaning. So in a VSAM file, the records are typically processed sequentially starting at a certain point in the file, let's say with a certain purchase order. And so purchase order line items may not have an explicit number. It may just be that the first line item is the next record you encounter after the purchase order header, and the second item is the next record after that, and so forth. That may not be externalized in any way, That just may be the way that the data is organized, and that's the way that the COBOL program expects it to be organized and processes it. Well, if I move that to another data repository, like a DB2, the order of the data is not maintained. The data could be come back to me in a couple of different sequences, depending on whether the data has been retrieved before, whether I'm using an index, and so forth. I may have to account for that in terms of modeling in my data. And then finally, dirty data. Um, um, I'll go into that more detail later on. But this is what the three different varieties of VCM files that I mentioned before look like, and the KSDS in the middle with an index component, and then being able to look up the data. Again, very fast and very efficient, and has served applications well for a long, long time. There are some other file types: physical sequential data sets and partition data sets. Physical sequential data sets are flat files that we know from a variety of different platforms. Partition data sets have a directory and then members, which are typically have an affinity together. So I may have a PDS that contains a bunch of JCL files, or a bunch of copybooks, or a bunch of COBOL programs that are all related in some way. Again, the schema for things like the physical sequential data set, or the PS, is embedded typically in an application program, might have multiple schemas. The physical sequence of the data might have meaning, and there might be dirty data. So the same problem that I called out with VSAM may be inherent in these other files as well. So I'm going to shift gears here for a second and talk about data provisioning. So how do I get this data? How do I get access to this data? One of the challenges in the project that I worked on with Clark and Andrew is getting the data from where it exists today in ZOS in either physical sequential data sets or VCM files, and getting it into DB2. So we had a couple of different methods for doing that. One is traditional extract, transform, and load, or ETL. And a tool that we looked at and may yet use is IBM's information server, known by its components, data stage and quality stage. This was an IBM acquisition about 2 decades ago, still very robust platform for ETL. It was one of the products that was rated in the Gartner study that Kim referred to in her presentation. The use case is periodic or batch-oriented movement of data. My data changes once a day. I do a bunch of updates to it, and then I want to distribute that data to DB2 for ZOS for analytics or querying. There are 2 stages within data stage which meet this requirement. One is known as the complex file format, and the other is the DB2 connector stage. The CFF actually ingests COBOL copybooks, which can be used for formatting, and they deal with, to a certain extent, some of the complexities that I mentioned of having multiple schemas for a single file. That's why it's called a complex file format. The DB2 connector actually allows you to bulk load data from that are being extracted from the VCM files or the physical sequential data sets, and then bulk loaded using the load utility that we'll talk about in a second. So let me pull up a diagram. This is actually at a very high level explaining what we're talking about. I start out with source files, and the legend is over here on the right. The blue portion is source files residing in the ZOS operating system. The yellow part in the middle is where data stage or information server lives, and that's on Z Linux. That could be in an LPAR, could be under ZVM. And then the green part is ZVM, which is where Red Hat OpenShift lives. Pardon me. The reason that I have this in a dashed line box is that one day Red Hat OpenShift and information server will be able to be co-located directly in Red Hat OpenShift in containers. IBM is not there today. They don't have a stated delivery time, whether that's going to be within the next year. But this is obviously the direction that they're moving in. So it's a little bit more complex today than it will need to be, but that's the way that it exists right now. And then on the right-hand side is the DB2 for ZOS repository that I want to move all this data into. The arrows connecting all these boxes are the hypersockets. The legend is in black down here. So I'm going to use the same color scheme and the same sort of metaphors for showing how all these components go together. But the first one we're looking at is moving the data from ZOS source files using information server and then delivering that to DB2. The reason that Red Hat OpenShift is included here is that the customer had very specific data conditioning that needed to be done. If you want to think of it in terms of data masking or business logic, you can. But they wanted to write that in Java and they wanted to have it run in Red Hat OpenShift. And so data stage would actually invoke using a Java stage, the Red Hat OpenShift in another container. Now, the other diagram that I want to spend a little time on is one that I discovered in the midst of this journey in the last 3 months. And I thought this was pretty cool because I had never seen anything like this before. As any DBA will tell you, the best IO is the one that you don't perform. So one of the things that we do in DB2 all the time is IO, or input-output operation execution, IO execution, and we try to avoid that at all costs. So going back to the preceding diagram, one of the benefits of using information server is that it is specifically designed not to land data on disk in intermediate steps. I could read the source file, I could drop the data in DB2 for ZOS and never have it executed as an IO operation on disk in any of those platforms. I would read it where it exists, and then it would go into DB2 for ZOS in the end, and those are the only times that it would reside on disk. There is no intermediate instantiation of the data, which means that I save a lot of IOs, I get a lot better throughput, and I get a lot faster end-to-end execution of those processes. So in looking at the bulk load for DB2 for ZOS, we can see the data stage server over here that's doing two different things. First of all, it is taking the data that are output by data stage and says this is the data that's ready to go into DB2 for ZOS. And it's actually using an FTP client that runs in data stage, and it's provisioning this data into Unix system services pipes. That's the USS that you see there. So I don't have to land the data on disk. I'm actually using a communication pipe and sending it over to that pipe. That's step 1A that you see there. Once all my data is provisioned into the USS pipes, I can execute step 1B, which is going to invoke an IBM DB2 for ZOS stored procedure. In this diagram is called DSN utils, DSN UTILS, but has actually been converted to more recently DSN util U. So by using this stored procedure, the stored procedure will actually retrieve the data that has been provisioned in the USS pipes, and then we'll execute a DB2 load utility that you know and love that you've been using with JCL forever. Same parameters, same formatting, everything is the same except that you're using the stored proc. So the benefit is I'm not landing the data on disk, and I'm getting all the benefits of the load utility. I don't have to log. I don't have all the overhead of firing off the data formatting other than the most basic. I can't put alphanumeric characters into a numeric field, but I can load the data very, very quickly and format pages at a time as opposed to inserting a row at a time with all the overhead that entails. So a really cool way that Data Stage does this. And as a matter of fact, you can do this yourself. You can actually roll your own to do the same things that Data Stage is doing. Why do I call that out? Well, management may say, we're not going to invest in a new tool in the mainframe. We don't have the budget to do that. So the technique that I just demonstrated there can be used as well. So the other thing that we needed to do for what I'm calling do-it-yourself ETL is we need to get the data out of ZOS to be able to be examined by this data conditioning application and the data masking application. So we can use something called the ZDSFS Linux command to mount ZOS volumes and be able to read data directly from ZOS in a Linux, either in Z-Linux or in Red Hat OpenShift. So it enables us to, again, read the data without having to FTP it or move it to another platform. So if you were going to do this with, let's say, a Linux platform that's running on a commodity x86 processors, you'd have to transmit this data probably using FTP. I have another customer that's using something called NDM for network data movement. But the bottom line is it's coming from disk and it's going to land on disk, and that's expensive. So by using ZDSFS, you can read a physical sequential or PDS directly from its location today in ZOS and then move it into your application on Linux without having to FTP the data. It mounts a ZOS direct access storage device. It reads physical, sequential, and PDS files natively. There are some limitations. Number one, it's one way. It's read only. I can't write to a ZOS disk mounted by ZDSFS. It does not enforce ZOS authorization. All of the ability to look at the data that is managed internally on ZOS is bypassed. So the recommendation is the only thing that you put on these volumes that are mounted via ZDSFS are files that are transitory files that you are going to be ingesting in this application. You wouldn't just allow any volume, any disk volume to be mounted. There's no catalog access. You have to specify specific volumes as if you were mounting a disk, and a file cannot span volume. So there is a physical limitation on how big a file can be to use this technique. The other data provisioning for what I'm calling the do-it-yourself ETL is a new feature available in Db2 called the DRDA fast load. This is allowing you, if you have to land data in Linux or in Red Hat OpenShift for whatever reason, to load that file directly without having to FTP it back into ZOS in order to load it using JCL into a Db2 for ZOS table. So there are a couple of prereqs. Number one, Db2 for ZOS. Number two, in Linux or Red Hat OpenShift, you're going to have to install one of these two components, the Db2 for LUW call level interface or the command line processor. And these clients are free, so there's no cost associated with that. And then you'll execute what is now known as the zload command. So it uses the same bulk load capability that we talked about earlier. It's not provisioning data via USS pipes, but it is reading the data natively directly from a Z-Linux or a Red Hat OpenShift file and loading that directly by executing the sysproc.dsn util stored procedure. You can invoke that directly from Red Hat OpenShift. You can connect to Db2 for ZOS as a client, and then you can issue the SQL call statement, and it'll execute this procedure. 100% of Db2 DRDA fast load is offloadable to the zip processor. So we talked about in the beginning different processors and their cost perspective. We are taking all of this load processing off of the general purpose processors, which the capacity of which helps IBM calculate your software costs, and we're moving it into the less expensive zip because this is a DRDA process, distributed relational database architecture, so it's coming from off platform. So the net of this is I'm loading a file that resides in either Z-Linux or Red Hat OpenShift directly into Db2 for ZOS using a Db2 for ZOS stored procedure, 100% zip offloadable. So this is what this looks like. Again, at a very high level, using the same color scheme. This is do-it-yourself ETL, and I can start with source files, use the ZDSFS to mount the source file for physical, sequential, or PDS data sets, and then use the zload to pop that data directly into DB2 for ZOS. So before I move on, I'd like to take another opportunity to let you ask some questions. Any questions about data provisioning ETL that I've talked about so far? Either raise your hand or pop it into the chat. I think we're okay so far, so I'm going to keep rolling. So the next data provisioning method is using replication, and I'm sure many of the shops that are represented here today on the call use some form of data replication to move data around from the mainframe to someplace else, whether someplace else is someplace else on the mainframe or to another platform entirely. The use case is near real-time consistency between source and target. So if ETL is batch-oriented, data replication says we need to have it there almost as soon as a transaction occurs for either analytics, for high availability, for workload distribution, and a variety of other means. There are a lot of flavors of replication. The two that I'm going to focus on here are the classic change data capture for ZOS that allows me to replicate the IMS and the VSAM data sources that we talked about earlier. This runs natively on ZOS. It executes on the general purpose central processor, so it may be expensive, and it is log-based capture, which means that for IMS is automatically logged, but VSAM needs to be set up for logging, and you typically do that if you're running CICS transactions, but even batch VSAM files can be logged outside the scope of this discussion today. But in order to use VSAM replication, you have to set up logging for the file to be replicated. Now, there's another wrinkle to this that was just announced this year, and that is the IDR VSAM for ZOS remote source, which means that I can get all the benefits of replicating VSAM files. It'll give me a minimal footprint on ZOS. It is actually off-shifted or offloaded to another platform. In this case, first of all, this is the classic CDC for ZOS with IMS and VSAM as the sources, all blue, all running natively on ZOS. Still uses hypersockets to get it across if you're running DB2 for ZOS in another LPAR on the same frame. And this is just another diagram explaining the classic CDC, the capture and apply. But this is what I was talking about in terms of the VSAM remote source, meaning that the VSAM files reside on ZOS, again here in blue. The Z-Linux today and sometime in the future on Red Hat OpenShift, I will be able to run the remote capture and offload a significant amount of processing. IBM tests have shown anywhere between 30 and 50% of the CPU utilization of the replication will now run on Z-Linux, which would be IFLs, or eventually in Red Hat OpenShift, and then loading that data into DB2 for ZOS using one of the techniques such as the DRDA fast load. So this is a way that you can reduce the processing footprint for VSAM replication on the mainframe if you need to get that data into DB2. There is finally another data provisioning method that I want to talk about in terms of completeness, and that is IBM's Data Virtualization Manager, or DVM. If you've ever used IBM's federation technology, started out a long time ago as something called Data Joiner. Basically, this is a federation product that runs natively on System Z. It accesses a variety of data sources in place, including both mainframe and non-mainframe, and other vendor databases or repositories like Database or IDMS, and non-mainframe data sources like DB2 for LUW, SQL Server, or Oracle. Even though it runs on the mainframe, it is 99%, up to 99% zip offloadable. So again, I can avoid the heavy hand of the central processor utilization by employing something like DBM. The APIs that I can use to access this data are HTTP, SOAP, SQL, NoSQL, and even REST with the ZOS Connect EE. DVM is actually a prerequisite for data stage to directly access vSAM files. Otherwise, I have to use FTP between the source files and the platform on which I'm running data stage. So here the diagram is shifted a little bit in that the arrows are pointing in the opposite direction. My request is going to occur over here in green in Red Hat OpenShift. I need access to this data. And let's say I write in my Java code using REST or SQL or something like that. It goes through Data Virtualization Manager, which reads the vSAM files. All blue here in the middle, but the DVM is zip offloadable, so you can save some money. Here's the screen that we saw before for Gartner, so I'm not going to stay on this. There are some quotes in the presentation slides. If you don't look it up, it is available. We can get it for you. It is publicly available now. But if you're considering either IBM replication or the ETL that is covered in this study, it's just about a year old right now, very current in terms of IBM's strength. So before I move on, I'm going to stop again just for a minute before I go into data source considerations and give you the opportunity to ask any questions that you might have. Either raise your hand or pop it into the chat, and we just have a few more minutes to go for me to wrap this up. But I did want to talk in some greater depth about some of the problems that people run into with mainframe data, expanding on what I talked about earlier. Okay, not seeing any burning questions. I'm going to keep rolling and give you a chance at the end. So the data source considerations. First, start with some of the problems that I outlined before. Purchase order header and line items, multiple formats of data appearing in the single file. I could have multiple COBOL copybooks in a COBOL program, for example, appearing both in the file section or in the working storage section. I may read it into the file section that has one copybook and then may move that record type to working storage, which has a completely different format and a completely different copybook. So it's like following a trail of breadcrumbs to find out what your data actually looks like, and that can be very confusing for people who aren't used to using data management, data repositories that way. The other things that can make this more complex are things like the redefines clause, which says that this is the data element as I see it. Oh, by the way, it may actually appear this way. So I may have a data element that's 80 characters character field, but it's actually redefined to be 24 character fields, which are actually binary data or computational data that's stored in binary format because they're all integers or something like that. This is something that is parsed out within data stage using the complex file format stage. So it gives you a leg up. But the folks that do this need to understand how all this works, and they may not all have a mainframe background. Going to talk very quickly about different data encoding schemes, whether it's EBCDIC, extended binary coded decimal interchange code, or ASCII. Notice here I have just a couple of representations of characters A, B, and C and what they would look like in hexadecimal. Hexadecimal C1 is the letter A in EBCDIC, hexadecimal C2 is B, and hexadecimal C3 is the letter C. If I'm using the ASCII data encoding, American Standard Code for Information Interchange, the letter A is now 4-1, not C1. B is 4-2, and C is 4-3 in hexadecimal. So for letters and numbers, 0 through 9, A through Z, this all works pretty well. Where things get wonky is when you're dealing with special characters that don't fall into that. ASCII natively only has 128 character set. It is 7-bit with 1 parity bit. And the most important takeaway here is that the collating sequence is different. If I sorted the data natively on ASCII, numbers come before letters. If I sort data in ascending sequence natively in EBCDIC, letters come before numbers. So if I have a coding scheme that allows a product number to be ABC123, that would appear in different places when I sort that on EBCDIC than it would in ASCII. And again, the sequence in which data appears may be meaningful. So you need to be aware of that if you're moving between native data on system Z, the blue boxes that we've been looking at in the diagrams, and I move to something else, either the green or the mango color for Z Linux or Red Hat OpenShift. Finally, there's Unicode. Unicode presents a whole different set of problems because Unicode is an international standard that allows for up to 48-bit representation of data, up to 6 bytes of 8-bit characters. Now, the problem with that is that the way that Unicode is able to represent today, according to their website, 143,000 different characters, is that they grow the number of bytes that represent a character. So a character that may be represented by 1 byte in EBCDIC, like the cent sign, the C with the vertical slash through it, is represented by 2 bytes in Unicode. Now, the problem that we have with that is if I have a 5-character field in EBCDIC in a file on the mainframe, when I move that to another platform using Unicode, now that 5-character field is going to be 6 bytes long if they included the cent sign in the 5-character space. And some of you may be saying, who would ever do that? And the answer is, I've seen customers who allowed their customers, their end customers, but I've seen enterprises where people would use the cent sign as an identifier because it was available on the keyboard and they liked it. And it was a financial services industry customer. So they embedded the cent sign in their identifier for accessing their account. And they had all sorts of problems because these files that were represented, these fields that were represented in 5 characters expanded. So I take a 5-character field, I want to move it to Db2 for ZOS, and I put in the data definition language statement that creates the column character 5, and the data won't fit. And if you don't know this about Unicode, you could spend weeks trying to figure out that problem. And I've known people who spent weeks trying to figure out that problem because they didn't understand the way that Unicode works. So some other data considerations. I mentioned the physical sequence that the data appears in a file may be significant. DB2 will not load or retrieve rows in a particular sequence unless that sequence is specified, like a SQL order by clause. So it might require that you add a record sequence number attribute where one doesn't currently exist today in order to maintain that sequence when you're moving data, let's say, from a VCM file into DB2. Dirty data, I've seen it all. It's pretty amazing the type of stuff that can be in data. What do I mean by that? Well, dates are always a challenge because many older mainframe systems may have 6-character dates. They may have dates that are comprised of a 2-position year and a 3-position Julian date. There may be 6-character dates, 2-position year, month, day, but they might have April 31st because the data typing was not enforced specifically. So all of these can be a problem when I'm moving from something like VSAM, which had very weak data typing because that was enforced at the application level, maybe in a copybook that could have changed over time. We have historical data that was put in that file maybe decades ago. I have customers, one hospitality customer that has a point system for people who stay at their properties frequently. They have data that dates back to the 1980s. And I asked them what their data retention period was, and they said forever. They want to be able to maintain this data, and that's their business, and that's the way they want to run it. So you may have legacy data that was created 30 years ago under a completely different set of considerations and have to put that data into DB2 today, and you may have some problems because of it. The other thing to be aware of is that special characters might wreak havoc with data loads if I'm using delimited files. Delimited files is I separate each field and each record with a special character. So I may use commas to separate fields. I may use vertical bars to separate records. What if there is a comma or a vertical bar in, let's say, a description field or a comment field? It'll cause my load to blow up because it's going to say there are too many fields here. So the delimited load would scan the data and says, I see what should be 5 different fields, but now there are 6 because there was a stray comma in a comment or a descriptor. So consider using fixed column formats for loading data if you're loading this legacy data into a repository that uses strict data typing like DB2. So before I get to putting it all together, I myself have 2 polls that I'm going to punch up here really quickly. Let me see. I'm going to open. I have 2. Actually, I have the same poll twice. I'm not sure why that happened, but I'm going to go with the first one that says, what are the inhibitors to using tools like DataStage, IBM Data Replication, and Red Hat OpenShift on System Z? And I'm going to go ahead and launch that right now. If you could take a moment to fill it out, the answers are, or the potential answers are, the CIO, CTO says we're moving off the mainframe. Management says there's no budget for investing in mainframe software, the complexity, or hard to find skills. Okay, I'm going to go ahead and close that down. If I'll give you another few seconds to complete your response. And so we're seeing answers all over the map. About 20% for the first. CIO, CTO says we're moving off the mainframe. Almost 50% management says there's no budget to invest in mainframe tools. Almost 40% the perceived complexity, and a full 50% says it's hard to find resources skilled in the technologies. So that's the one that I can help you solve, I believe, is the 42%. Management says we're not going to, we don't have the budget to invest in mainframe tools. You may consider using the what I call the DIY or the do-it-yourself ETL tool. And then the second poll that I wanted to go ahead and bring up is, what are the technical inhibitors to using the tools and techniques that were presented today? Pardon me. So I'm going to go ahead and launch that poll really quickly. One is the complexity of integrating the tools, and the other answer is the complexity of the data that exists in your shop. Getting a lot of good feedback. Again, these can add up to more than 100% because multiple problems may exist at the same place. Interestingly, 90% say the complexity of integrating the tools are an inhibitor. So this is great feedback for IBM. It needs to be simpler if it's going to be consumable and people are going to be able to deploy it. And then another 40% say that the data complexity is an inhibitor for all the reasons that we talked about. Multiple schemas in the same file, the dirty data, etc. So that is about it for me. I'm going to go ahead and close this poll and I'm going to do my wrap up. Some people may find this a little cheesy or a dodge, but I thought about it a lot. And the biggest challenge, I think, are communications. I have these 10 smiley faces up here, all the different roles that may be included in a project like the one that I collaborated on with Clark and Andrew Austin. And that is the fact that we need people who are familiar with components on Db2 for ZOS, whether they're a Db2 for ZOS DBA, a COBOL programmer, a business analyst, folks that are data stage administrators or developers on ZVM, aka Red Hat OpenShift, Java coders, and a Red Hat OpenShift admin, or somebody who is a communication specialist tuning the hypersockets. Hypersockets are like anything else. There are different parameters that can be used. And I read some posts on the IBM technical sites that said that if you don't use the right parameters, you're going to get terrible performance on hypersockets. So having to configure all that takes some time. And all of these different perspectives, all of these different people coming from different backgrounds with different experience are going to need to work together to a common goal. And that's a challenge. It's hard to get people speaking the same language and being able to understand the same challenges. So that would be the thing that I think is going to be the greatest inhibitor in my perspective, is getting everybody to sing from the same songbook. So with that, Kim, I hope you're still there because I'm going to go ahead and wrap it up.
I am still here.
Excellent. Contacts and resources, that would be you. The Fillmore Group can assist you on this journey with both professional services and training, whether it's architecture and implementation, health checks, version upgrades, or IBM authorized training. Kim's email address is there. And some resources, a lot of the things that I talked about earlier, I have links here so you can look them up. Mainframe hardware processing units, hypersockets. There was a great post on DeveloperWorks explaining the data stage bulk load, the one that took data and provisioned it on USS pipes and then consumed it by issuing a SQL call to invoke the DSN util stored procedure. That article is there. It is fascinating because it was never anything that I considered before. And this is all stuff you can do yourself without data stage. You can just follow that pattern. The DB2 fast load is included in the DB2 12 for ZOS performance topics. That's an IBM Redbook. And with that, I would like to say thank you to everyone who hung in there today. Most of the people who started the day ended with us. There is a brief survey as you log off today. We would appreciate the feedback for the content and the presenters that you heard today. And Kim, I'll give you the last word.
Okay, well, Frank, that was a wonderful presentation. And I'd like to thank you, and I'd like to thank Andrew, Clark, Elton. I mean, everybody did wonderful presentations. I hope this was valuable to everyone who's attended. And we look forward to doing another meeting. If there is any topics that anyone is particularly interested in, please let me know. And of course, as I asked, any feedback on replication monitoring, I would really appreciate getting. And I think with that, yes, please complete your survey. We will post the recordings on our blog sometime over the next few days. And I think that pretty much does it. Anything else, Frank?
Just the materials will be there as well as the recordings. Somebody had asked about the presentation materials, and we'll have them from all the presenters up there so that you can look them over and share them with your colleagues.
Definitely. And someone else who also deserves some credit, whose name I do not know, but whoever designed all the slides for Red Hat is really awesome. I'm incredibly jealous of the professionalism of their work. I think it's a wonderful alliance with IBM, and I hope it's terribly successful. So everyone, thank you. I think with that, I will ask you, Frank, to end the webinar.
Okay, take care, everyone. Stay safe and healthy. Thank you.